Hey everyone, with this APC video, I'm going to focus about derivatives. And in particular, I'm going to tell you how do we find the derivative of polynomial functions, trig functions, how to do second derivatives, applications of derivatives such as the definites and then the max values, and also how to write up differential equations. As I mentioned before, for those who have already taken AP Calc, while these first four you don't really need to relearn, the writing of differentials is going to be a new aspect, so definitely make sure that you pay attention for that. Now, what are the types of equations that we need to do derivatives for? As we mentioned, we have to be able to do for polynomials and trig functions. As a refresher, polynomials are equations that are written with this format of something times x to some power plus something to x to some power, so on, so on. On the other hand, trig functions are things like sine and cosine. In particular, we're actually only talking about sine and cosine. Now, there is a small chance, very small, that you may have to do derivatives with logs, ln, tangent, whatever. However, I'm not really going to focus on it because the chance of it popping up is very small. And honestly, if it does pop up, just bite the bullet, lose those points, focus on everything else. Again, for those who already know it, whatever. The reference table actually does put all the derivatives on there, but it can be confusing for those who haven't actually already done it before. So how do we do derivatives for polynomials? It's actually really easy. There's two steps. You're going to multiply the coefficient by the exponent, and then you subtract 1 from the exponent, and that's it. So for example, if we had an equation like 5x cubed minus 7x squared, and we want to take the derivative with respect to x, first we would write it like this: d over dx of 5x cubed minus 7x squared. What we're going to do is we're going to take these exponents, 3 and 2, and multiply their coefficients. So 5 is going to be multiplied by 3, 7 is going to be multiplied by 2, as we see here. And then what I'm going to do is subtract the 1 from both those exponents after they get multiplied. So we get 5 times 3, which is 15. 3 minus 1 equals 2. And so far, and for the next part, it's 7 times 2 is 14, and 2 minus 1 is 1. So I end up getting that the derivative of this expression is 15x squared minus 14x1. Notice how the size, the power of that big x, the main x, always goes down by 1 every time you do a derivative of a polynomial. And that's it. That's all you have to do when you take the derivative of a polynomial. Now let's see a different case. Let's say we had a scenario like this, where we have 4x plus 7, well, 2x squared minus 4x plus 7. Well, this one's easy enough. We take the 2, multiply the coefficient to get 4. We subtract 1 from this exponent. What about this? Well, remember that there is that hidden 1 exponent. So the 4 gets multiplied by the exponent of 1, and then we subtract 1 from that to get 0. But what about this? There is no exponent. Well, yes, there is. Technically, this could be written as 7x to the 0 power, because anything raised to the 0 power is 1, so x to the 0 is 1, so it ends up being the same thing. So that power of 0 gets multiplied by 7, and it basically drops out. So what we end up with, the derivative of this function is now going to be 4x to the minus 4, and then there's nothing here. So this is actually one very important thing to note and keep in mind, is that whenever you take the derivative of a constant term like 7, 5, whatever, just a number, there's no x term, it always ends up being equal to 0. This is actually another reason why this notation is so important, is because later on, not in this course at all, but in later on in calculus and physics, you will come across equations that have multiple variables. So this is telling you which variable is an actual variable as opposed to something else. So if this had another variable like b next to it, you would still consider it a constant if you're taking the derivative with respect to x. All right. Now, how do you find derivatives of trig functions? I apologize if the bottom part gets cut off, but the way that we find the derivatives of trig functions is pretty much, it's a little bit more complicated, but at the same time not. Once you get the handle of it, it becomes pretty straightforward. So first what you have to do is multiply the coefficient by the derivative of the inner part. So for example, let's say we had this as our function, 4 sine 2x. 2x is inside the sine term. What we would have to do is take this, find the derivative of this, and then multiply the coefficient. Well, the derivative of 2x, as we just saw before, is just 2. Now, the reason why I said that this is, can be a little bit tricky, because I know that sounds weird, but the one thing to point out is that the inner part of the sine term should almost always be like something like this: 2x, 3x, 7x, basically a number and x, and that's it. So you're pretty much going to, another way of phrasing is that whatever number is in here, that multiplies the coefficient. So now in this case, we have a 2 multiplied by 4, boom. Now there is a second step, and this is actually where it gets a little tricky, is that you have to replace the term with its derivative term. And for the most part, this sort of requires some memorization. But again, the reference table actually does have a lot of this stuff. In this case, the sine gets replaced with a cosine. So putting this all together, if I want to take the derivative of 4 sine 2x, well, I multiply the 4 by 2 to get 8. I replace the sine with cosine to get 8 cosine 2x. Notice that the inner part does not change in here. I don't do the same thing as the polynomial where I subtract 1 from the exponent or I change anything. It stays the same. The only thing that changes is the coefficient term and what the trig term is. Now, like I said, you do sort of have to, I mean, it's helpful to memorize it, even though you do have it on the reference table. Uh, it's useful to save time. The derivative of sine is cosine. So if you're taking the derivative of the sine term, you just replace the sine with cosine. Cosine gets replaced with negative sine. So it's easy enough to remember that sine gets replaced with cosine and vice versa. Sometimes it can get a little tricky knowing whether it's going to be negative or not. Now, what about second derivative? It's easy enough. It basically means that after we take the derivative the first time, we just do it one more time, and we take the derivative of the derivative. So before we had this equation, and we found that the derivative of it was 15x squared minus 14x. So what we could say is that the second derivative of this is just the derivative of the 15x squared equation, which would be, well, take the 2, multiply 15 to get 30, subtract 1 from 2 to get 1. Uh, there is no exponent here, so that x just drops out, and we get 30x minus 14. All right. Now, what are some applications for derivatives? As we mentioned before, well, one of the things that you could do is find the value of the derivative. So a lot of times what we do is you do the same step, you just take it, there's just an extra step beyond subtracting 1 from the exponent or whatever, or replacing the trig term. For example, if you want to find the derivative at some point, like basically what the slope of the line is at a certain point, what you would do is just plug in what the value is for whatever term you're using. So for example, if I want to find the acceleration at 2 seconds, let's say, and this was my equation, and I had to take the derivative, I would take the derivative. I get 19t squared plus 12t. So far, so good. And then I would just plug in 2 for t squared, or for t and t squared, and I'd end up with 60. And that's it. So I'd end up with a numerical value at the very end. Now, the other application is doing min and max. As I mentioned before, I mentioned this in the previous video, that this is just done by setting the equation equal to 0. So what you can then do is, again, once you get to that equation, you set it equal to 0, and then you just solve for t, divide both sides by t, get 9t equals negative 12, and we get that t equals negative 1.33 seconds. So this would tell me that at this moment in time, this graph either hits a minimum value or a maximum value. Now, unfortunately, without doing some little bit of extra work, I can't figure out exactly what it is. Oh, it could also be neither, but that's neither here nor there. The one way that you could do this is by actually finding the second derivative. Um, but like I said, you can actually do this all with your graphing calculator. Just plug the equation into the graphing calculator and just look to see whether there is or is not a min or max value. In fact, the graphing calculator will actually tell you what the min or max values are. Now, what about the differential equations? Now, this is actually a very specific question that pops up on the APC exam, and you definitely want to make sure you know how to set it up. It actually is not that difficult. So the way that question gets worded, the way you're actually supposed to approach it is almost through algebra. So let's say we had a scenario like this, where they tell us that there's a frictional force acting on an object equal to negative BV. And we're told that there's a gravitational force of F equals mg. Now, we may not have learned about Newton's laws or forces. That's fine. You'll learn about it. So this will make a lot more sense later on. If you want, you could rewatch it. But if we use algebra, what we'll end up being doing is doing this. We use the equation F net equals ma. This is a very standard equation. Well, we know that F net is just adding those two forces. So I end up with mg minus bv equals ma. Now, the question will say, uh, using Newton's second law, which we just did, then we'll say derive a differential equation. So it will explicitly say it wants a differential equation. Well, so what do we do? How do we turn this from an algebraic equation to a differential calculus-based equation? Well, what I do is I see that there's a v and an a here. I just replace a with, I made a mistake here. That should be dv over dt. So I replace acceleration with the differential version, which is that it's the derivative of velocity with respect to time. So I'd end up with an equation that says mg minus bv equals m dv over dt. And that's it. If the equation on the left-hand side had an x instead, then I'd replace the derivative of the acceleration with the second derivative of position. How do you know you're supposed to do that? Like I said, it comes down to experience. And when you do a few questions, you'll start to get the hang of what exactly you're supposed to be looking